Hello boys and girls. This video is the starting point to a whole bunch of videos and topics that I would want to talk with you about and see some discussion, and that is the Curry-Howard correspondence. And I kind of give a soft intro today and will in future videos try to extend upon that. And here in particular, if you have any questions, then write in a comment, let me know, so that that the idea gets across, because it's pretty deep. We have a connection here between raw logic, if you want, and language theory and how they come together. And well, I will just get into it, right? So on the upper half of this board, I have some sentences written down in logical language, propositional logic, and here down there's some basic play with functions. All of them are pretty easy to grasp, I suppose, and if you don't know the ideas in the Curry-Howard correspondence, then this will give you a connection today between these two. So on the one hand here, for example, I have written down this proposition, which is tautology in propositional logic, classical propositional logic. And namely it states that if you have three propositions, I call them P, Q and R, and the left hand side of this sentence is true, then this implies also that the right hand side is true, or in the other way around. And the statement is, the claim here is that if P and Q holding implies R, then also P holding implies that Q holding implies R. So I give you an example. If P means it's raining, and Q means I'm outside and not at home, and R means I'm wet, then you could read this proposition as, if it's both true that it's raining and that I'm outside, then I'm wet. This is one claim, and this claim, whether it be true or not, I mean I constructed it in a way that it seems reasonable, and we take it as a true statement. Then this implies that if it's raining, then this implies that if I'm outside, I'm wet, right? So if it's raining, then this implies that if I'm outside, that implies already that I'm wet. And here in the other way around, that also holds true. So I don't know, if let's choose some other propositions here. If I have a pet that is a cat, and I have my meat on the table, then it's going not to survive the afternoon, let's say. I just made that up, right? So the statement would be, if you have a cat, then if you have meat on the table, the meat, like let's say no food will be on the table in the afternoon, let's say that's the statement. Then this is equivalent really with, if I have a cat and there's meat on the table, then there will be no meat on the table in the afternoon. Okay, so I mean, if I choose these examples, they are like almost so obvious that it's hard to see the almost difference in the statements. But if we were to, I mean, I could cook up more examples, but I don't want to dwell too long on that. Basically, this is simple to prove also statement in propositional logic, and I give you some other examples. This statement is also a tautology. It says if a proposition holds, then that proposition holds. For example, if I make YouTube videos, then I make YouTube videos, right? Okay. And then thirdly, here in the proposition it says if P implies R and Q implies R, then given either P or Q, R is implied. So for example, okay, let's say I go on vacation and whenever I go on vacation, I spend a lot of money and hang out on the beach and buy a lot of drinks. Then, if I go to Spain, I will have no money at the end of the day. And also, what also is true, if I go to Portugal, I will have no money at the end of the day. So, if either holds true, that either I'm in Spain or in Portugal, I will not have money at the end of the day, right? So that's one proposition, and a very related proposition is the one down there. It says if not P holds, so the negation of statement P and the negation of statement Q, then the proposition either P or Q also does not hold. So for example, if P means I can fly and Q means I can see through walls, then if I cannot fly and I cannot see through walls, then it's also not the case that I can do either of these things, right? Very simple. And in these examples that I did now, I always made it so that the proposition on the left hand side is happens to be true, and so the right hand side is implied. But as the propositions, these propositions also hold true if the proposition that this proposition is made of are not true. For example, if P means I'm wearing a t-shirt, as I do, and if Q means I have dark hair, then the statement would be if I was not wearing a t-shirt and if I didn't have dark hair, then it's the case that neither me having a t-shirt on or having dark hair is true. Right? So this implication is still true even if in this case now the propositions don't hold. But okay, so then this either side is basically just a language, a propositional language to formalize certain facts, and that has a billion applications and history of formalization of any formal science, really, from just math, physics, linguistics, and so on. But now I want to go to something a priori unrelated. Namely, I want to talk a little bit about types. And in that case, I talk about types of functions in particular. So what I start with here is I define a function f of x as x squared, right? And if I just write it down, if I just write down this expression, then it's clear that x must be something that I can multiply, but it's not already clear what the types of this function would be. There are many options. So I have written down a few options. So we might consider f as a function from the natural numbers to the natural numbers, or as a function from the real numbers to the real numbers, or from the natural numbers to the real numbers. In the second case, the codomain would coincide with the range of the function. Not really the point here, but there are some properties of the function that really depend on what type of the function you consider. What I mean is that, for example, in this case, this function would find a match for all values in the codomain of the function. So if you say, let's say you want to end with pi, then there's an argument, namely the cubic root of pi, that maps to pi. And on the other hand, in that case, the the range of the function would be very restricted. So if you speak, like the type is very interesting in that if you make a statement about a function, then it might depend very much on the type. I've also written down two other notes. So for example, this function as I've written it down here cannot be considered a function from the real numbers to the natural numbers, because there are many arguments, like pi for example, in the real numbers, that this function would translate to some other real number and not a natural number, so that doesn't work out. And also, I've given the function a name here, I called it f, right? But you can also speak of functions without giving them a name. So if you write in this notation with the arrow here, x maps to x to the power of 3, then you can consider this whole expression as a function and doesn't have a name necessarily. Okay, and then now here are more complicated functions. Here is a function which takes two arguments, so this x is the product. Says I take a natural number argument and I take a real number argument and put out a real argument. So g of that's not what I wanted. G of n and x here I would map to x to the power of n. Okay, this is just another function, except that the function takes pairs of numbers as arguments, and they're called n and x here. And you can also have higher order functions. So this function I would be a function which actually takes a pair as an input, so it takes also two arguments. And the first argument is a function from R to R itself. Right? So this function I is defined like that. I say I take some function h and some value x, and since in R I know a bunch of numbers that are there, for example the number 0 is there, I can make this definition so that I evaluates on a function h and then argument x as h of x minus h of 0. Right? So this is just as an example as a function that takes functions as arguments. And then I have a last example. It's also a function which takes function as argument, namely. And the point being here, so up until now I just used natural numbers and the real numbers as types to construct these function types. But now I get a little bit more abstract, and in a sense that we have seen that some expression doesn't in itself determine the type. We can also abstract away the type and consider the type. For example, you can consider the type a running parameter, right? So, and we might in a programming language, let's say Haskell or Idris, we might be able to write functions that don't have a specified type from the get-go. Or for example in C++ or C, you have function templates, right? And so for example, I may ask you to write a function from a generic type p to another generic type p. And you may think a little bit and then come up with, well, the function f of x that returns x, right? The identity function. It's a function from a whatever you take as the type p. There's a function called the identity function that maps some value of p, let's call it x, to p. And this function is also one where I didn't specify the type, but I leave it open. I call the type. Consider three type variables p, q, and r, and the function f should have for the following type. It takes as an argument. It takes as an argument a function that maps a pair where the first entry is of type p and the second entry is of type q. It takes this and maps it to a value of type r. So that's the first argument of f is this a kind of function of this type, and f with this function argument returns another function which is a function which takes an argument of type P and returns a function that maps an argument of type Q to a value of type R. Okay, so here I also wrote down the definition of the function that fits this type. So if K is a function of that type, so K is a function that takes two arguments, one of P, one of Q, and returns, if you pass these two arguments, a value of type R, then big F of K is, it has to be a function of an argument of type P. Here you have a capital P, here you have a small p, and the return value must be a function from Q to R. And so it takes a function as an argument and returns K of P and Q, and indeed by the definition of the type of K, this is actually a value that lies in R. So you saw that I just checked the type and it fits, right? And I give you here an example that if you were to take this G that we have defined before here and compute f of G, so this function takes now this G as an argument, which means we instantiate these types. So if this function is considered that it takes G as an argument, that means that P must be the natural numbers, Q must be the real numbers, and R must be the real numbers. And the output is then the function that maps n, right, a natural number, to a function that maps x, a real number, to x to the n, right? So that works out, and actually, if you take this function, so that if you take the value of f of g and the value at 3, then you get the function which maps x to the power 3, and that's actually f. So I go full circle here, and turns out with this function I can express the function f as the value of another function, right? Okay, but now comes the plot twist. The joke is that if you take these sentences in propositional logic and given certain axioms, namely those of constructive logic, then a logical statement is exactly then provable. There's a formal proof for that. If the proposition, the claim here, interpreted as type, has a term or a function that fits the type. So again, the idea is that, and we have seen, we have a complicated type here, and you might have noticed that that type exactly corresponds to this statement here. So there's no accident, right? Here you have a type, here you have a proposition, and it's just a matter of interpretation, basically, right? So you have this arrow here. It's to construct function types, and here it's read as implication. And you can take all the statements in propositional logic, and actually even in more complicated logic with quantifiers too, but another day. You can take all these propositions and consider these propositions that really, they are just syntactic expressions following some formal description of what you can do with all these gadgets in your logic. And if you take the same rules and consider them types, then the Curry-Howard correspondence says that for them to be provable, to find a proof actually, is exactly the same thing as programming or finding a function or some other type of these types that corresponds to that. And that's actually how, for example, theorem provers work today. So when you do automated theorem proving in some languages like Coq or Acta, then the way the program actually proves the proposition is by constructing a proof, but that proof is really just the algorithm that fits the type that corresponds to the proposition. And actually, if you have this this function that fits the type, then you can also interpret the function. You can interpret the widgets and tools that you use to construct function. For example, you know, this maps to error, to translate that to more close to natural language proof, right? So for this to work, you want actually to have also a very restricting language, in which terms you code, in which terms you write down proofs or functions, and that would be in that case some type lambda calculus. Okay, so I know maybe that's I'm not sure to what extent this short introduction is clear and what the implications are, but let me know in the comments. Subscribe to this video, and if there's some interest, I will cover some more insights in that direction. Take care.